I'm going to do an example of proving a statement related to vector functions is true. Now, in our journey of mathematics, a lot of what has happened before this course has involved theory or algebraic statements that were not too difficult to prove, and occasionally we would be just told to accept something as fact. But if you're in a third semester calculus class and you're going to take more mathematics, you're soon going to realize that sometimes formulas that we would just think, oh, that makes sense, it's probably right, sometimes those statements aren't always as accurate as you might believe. So this is not going to be a high level proof. It would be considered algebraic, probably something very similar to verifying a trigonometric identity, but we're going to use vector valued functions instead. So I'm using the component form of the vector notation, but really what this is this vector here, r of t, is some function I and some other function times j and some other function times k, if you would prefer that notation. I try to mix it up on my channel because you just never know what you're going to see moving forward. There are other vector notations besides these two, that's for certain. So I've got a three component vector function. Each component is its own function, as we've been studying. And then I have a fourth function that I'm going to call a scalar function, and you'll see why in just a moment, w of t. And here's the statement we're going to try to prove. If we take a single function and multiply it by a vector function and then take the derivative, will the product rule actually work even though we have a vector function and we'll call it, well, it's a scalar function, but a regular function? Does the product rule allow us to interact with these two? So this is what we're going to try to prove. There are multiple ways of going about this. What we're going to do is we're going to take this left-handed statement. There's the equal sign. This is the left-hand side. And I'm going to expand it out using some vector statements that we know work, some definitions and such. And then we're going to do the same with the right-hand side, this statement here. And we're just going to demonstrate that we get the same algebra on both sides. They are therefore equal to each other. So it's not going to be many steps, but here we go. So first thing, and this is our statement on the left-hand side here. This we'll deal with in a moment. So if I want to multiply a function times a vector, what that means is the function times the vector. I've written out the components of the vector here, and we're about to use scalar multiplication. All right. So w times f, w times g, w times h. All I've done here is scalar multiplication. Now, to take the derivative of a vector function, we've already seen this, you just take the derivative of each component. Well, now each component is a product of two functions, not vectors. This component here is just two functions, two functions, two functions. We are allowed to use the product rule of derivatives in this situation. And if we do that, we end up with the derivative of w times f plus w times the derivative of f as the first component. Now there's a comma, and then the derivative of w times g plus, leave w alone, multiplied by the derivative of g. There's the second component. Moving on to the third, derivative of w multiplied by h plus w multiplied by the derivative of h, and there's our third component. It's kind of a mess. It expands out pretty wide on the piece of paper here, but that's what we would be doing to try to prove this statement works. Now, we're going to go back and work with the right-hand side of the statement. Now, what was that statement again? Oh yes, well, that statement was if we multiply the scalar times the vector function, take the derivative, which is what we just did, we would get this statement here. So what is this statement here? What does that really look like? Well, where it says r of t, that would be the vector function. And where it says r prime of t, that would be the derivative of the vector function. That's just how we're told to take the derivative of a vector function. That was its definition. Now, moving along, we will do the scalar multiplication here and here. These are both a scalar times a vector, a scalar times a vector. And when we do that, we end up with, well, two larger vectors, w prime f, w prime g, w prime h, that's here, w f prime, w g prime, w h prime, that's there. To add two vectors, do you remember what to do to add two vectors? Well, we just add the matching components of the two vectors, and we would end up with this statement. Now, I won't say that out loud again. It's pretty easy to pause and compare that I've just added x, y, and z components of the vectors together. But here is the kicker. This statement, working with the right-hand side of our given formula we're trying to prove, this statement down here is exactly the same as what we ended up with when we were working with the left-hand side. That's it. They are the same. So that doesn't mean the proof is done, because just because you've algebraically done something and you personally have seen it, you need to tell the reader that what you've done is done. We need to put some form of a conclusion in there. Now, for purposes of a course that could go many different directions time-wise, I'm going to take a simpler route than maybe some other instructors would do. I'm just going to somehow indicate that the left and right-hand sides gave us the exact same expression, so the given formula was true. So you could abbreviate it: left hand side, left hand side, you could write that out, and right hand side are the same. Three dots. Therefore, the given formula is true. Alright, I'm pretty happy about that. Not much else to it. For my students, for example, our book has a number of similar types of statements that in the assigned problems in the book says prove each of the statements. These are all, or nearly all of them, done in this sort of algebraic manner. It may be possible to begin with the left-hand side and keep going till you end up with the right-hand side, but I'm allowing my students to work with both sides and meet in the middle, so to speak. All right. Until next time.